In this video, we're going to discuss graphing the cosecant, secant, and cotangent functions. So any discussion of cosecant, and we're going to do in the order of one cosecant problem, one secant problem, one cotangent problem, while explaining some of the theory behind why we graph it the way we do. So starting with cosecant, any discussion of cosecant, you should really understand, first and foremost, that the cosecant of x is the same thing as 1 divided by the sine of x. I'll put a little parentheses around there to make that clear. And so since sine and cosecant are so closely related, I'm going to draw the graph of sine on this existing graph of cosecant here. So here's a graph of sine. If you're not sure how to do this, go and watch the video I have about the graphing the sine function. Okay, but these points here are going to be on the graph of y equals the sine of x. Okay, so it's going to look something like this. And the graph of sine of x, it keeps going, right? All of these functions, all the trig functions that we're talking about, they are periodic and continuous. Or not continuous, but sine is continuous, and it keeps going on and on forever. They all keep going on and on forever. So, looking at the relationship here, notice that if this is 1 divided by the sine of x, so if sine of x equals 0, then we'll have a 1 divided by 0 situation, which whenever we have a 1 divided by 0 situation and we're graphing, how that is represented on the graph is as a vertical asymptote. So it's expected then that we would have vertical asymptotes whenever y is equal to the sine of x is equal to 0. So whenever the sine of x is equal to 0. Okay, so we have these vertical asymptotes here. The other thing to know is that the sine of certain things, like if I said this, right? If I said, what if I said this, right? The sine of x is equal to plus or minus 1. The values for x that you could give me here would be pi over 2, 3 pi over 2, etc. Essentially any odd multiple of pi over 2. It could be negative also. Okay, so what that means is that at these points, right, we have these shared values, these shared points. Because if cosecant of x is 1 divided by the sine of x, and sine of x is either 1 or negative 1, well, 1 divided by negative 1 is negative 1. 1 divided by 1 is 1. So these points are going to be shared. So using those two ideas for cosecant, both when the graph of sine is 0, we have vertical asymptotes, and when the graph of sine is either at its relative maximum or relative minimum values, then we're going to have shared points with the cosecant graph. Using that information, we can develop a strategy for graphing every possible cosecant function. So let's look at a somewhat nasty example of a cosecant function. All right, we're going to graph y equals -2 plus 3 cosecant of 1/2 x. And the way we're going to do this is to first actually graph sine. Okay, we're going to graph sine first. So, I mean, that's what we're going to do, but in order to get there, we still have to pull off the information from the function itself. Okay, so if we look at what's being multiplied by the function, this is the a value, and for sine and cosine, we call that amplitude. Now, amplitude is only really applicable for sinusoidal functions, meaning sine and cosine, but it's still the word amplitude that is, but the value of a has to do with the vertical stretch or the vertical compression of the graph, so we still call that 3, no problem. The period, remember that the period of cosecant is t is equal to the fundamental period of cosecant, which is 2 pi divided by omega. So 2 pi divided by 1/2 is going to be 4 pi. So 4 pi is the period for this. The phase shift would be whatever is being subtracted from the x. You look and you see that it's nothing, so there is no phase shift. And the vertical shift is whatever is being added or subtracted from the output, this being the output of the function. Well, cosecant of 1/2 x, right, is the output times all those values are multiplied by 3, but then we're subtracting 2. So this is a shift of down 2. All right, let's take a look here at the tick marks. For how we're going to label the x-axis here, and the way we do that is to take the period. So we're going to take the period and we're going to divide the period by 4, and we find that each tick mark is going to be pi away from the previous tick mark. And the first tick mark starts at the phase shift. Since there is no phase shift, we start at 0. We have 0 plus pi for So the first tick mark is 0, right? The next tick mark is going to be at pi. We take pi and we add another pi. We get 2 pi. And you'll see that the remaining tick marks are at the pi's, right? 3 pi and 4 pi. So now we'll just draw our graph. We'll draw our axes. Okay. Since we had a shift to 2 down, I'm going to kind of distort this. I'm going to kind of put the x-axis intersecting with the y-axis a little higher because I'm going to have more information below it. Now remember, we're going to graph sine. So let's label everything. We've got 0, let's say that's pi. It's about the same distance away. That's 2 pi, okay, 3 pi, and 4 pi. Okay, so there's our tick marks on the x-axis. Now vertically, we had a shift of down 2. So let's say this is 2. It's negative 2. Our amplitude is 3, so that means if we go about right there, that'd be our negative 5. That's 3 down from negative 2, and then we go up 1. I'll say up 3 to give us a value of positive 1. It is helpful to draw in a midline using a horizontal dotted line. We call this an equilibrium line or a midline, doesn't matter. And now what we're going to do is we're going to graph sine, and we're going to use our knowledge of how sine is graphed. So we start at the midline, the equilibrium line for sine. The next point on sine is up at the maximum. Then we go back to the equilibrium line. Then we go down to the minimum. And we go back to the equilibrium line. And this will be the graph of sine. Okay, you can draw this as a dotted line. This is going to be erased later, but we can draw it as a dotted line if you want. It's very hard for me to do that on this computer, so I'm just drawing it like this for now. All right, now going back to what we just talked about, whenever sine has a 0, or whenever it crosses a midline, or and whenever it has a minimum or maximum, we have shared points. So what we're going to do is just draw in the asymptotes. So we have an asymptote right here because sine crosses the midline of sine right there, and right there, and obviously also on the y-axis. The reason that this is because of this shift 2 down, right? This shift 2 down doesn't change the way that the cosecant function would still be undefined if we had an output of 1 for sine. So an output of 0 for sine. It's that shift down makes it so that we draw these asymptotes when we have these intersections across like the midline. It might be, the reason I mentioned that is because you might be tempted to put that like here and here, and like wherever it would be over here. That is not how you do it. All right, so at this point, all that's left to do is to draw in the graph of cosecant, and we know that how this works because it has this shared point there with sine, and we just go up like this. We draw these U shapes. Okay, these are not parabolas; they're just U shapes. Okay, and this is it. This is the graph of cosecant. Now, that's the graph, but remember that the sine graph here, this orange line we drew in, is not part of it. So you would want to go through and you would want to delete those. Oof, I don't know how to put that back. Sorry, that's going to be confusing. Okay, so that right there, those blue lines, that is cosecant. And you could keep going if you wanted. Okay, we would have another at 5 pi, right? We'd have a value of 1 right there, so we'd have another one of these guys, right? And it would keep going this way. And that's the graph. Right, secant, and very much the same, the kind of the same exact thinking here. We have the same stuff happening for secant like we had for sine. So like secant of x is equal to 1 divided by the cosine of x. So all the same reasoning. If this is the cosine of x, I'll draw that in really quick. Okay, this is 1 period of positive cosine of x. Okay, notice how when we had zeros at cosine, we had asymptotes, and when we had relative minimums or relative maximums, we had shared points. Exact same thinking here. So we do a very similar procedure here for graphing secant of x. We're going to start by graphing cosine of x with cosine of this stuff. So first of all, our amplitude we can see is just going to be 1. That's the number being multiplied, the absolute value of the number being multiplied by secant. We got to pay attention to that negative, but it'll come into play a little later. All right, the period, since omega is just 1 here, the period is just the fundamental period of 2 pi. The phase shift is going to be pi over 4 to the right. That's what this means here. The vertical shift is 1 up, and we're ready to figure out what our tick marks are going to be. Okay, so first step is to figure out how far apart the tick marks are going to be from each other. and that would be 2 pi, the period, divided by 4, so they're going to be pi over 2 away from each other. The first tick mark, though, is going to be at pi over 4, because that's what our phase shift is. 2 pi over 4, we're going to add pi over 2, and that will give us, what does it give us? That gives us, so we had, that would be, sorry, I'm confused. I'm confusing myself here, too. That's going to be 3 pi over 4. Okay, then to 3 pi over 4, which is the same thing as 6 pi, so plus, essentially, right, we're going to add 2 pi over 4. That's going to give us 5 pi over 4. Okay, then from 5 pi over 4, we're going to add another 2 pi over 4. 2 pi over 4 being the same thing as pi over 2. And that will give us a final tick mark of 7 pi over 4. So let's draw that now. I'm going to put this, we shifted one up, so I'm going to shift the horizontal axis down just a tiny bit. Okay, tick marks, so let's put those on the graph. The first one, let's say, is right here at pi over 4. Now, if pi over 4 is this far from the x-axis, from the y-axis, then 2 times farther than that will give us pi over 2. So let's say this was 3 pi over 4. Okay, and then again, this is 5 pi over 4. And one more, 7 pi over 4. Actually, we need another one, don't we? So if you add another 2 pi over 4, we'd be at 9 pi over 4 over here. All right, cool. Now we are going to graph negative cosine. Oh, actually, sorry, we haven't dealt with the tick marks on the y-axis yet. So we're shifted up 1. So if we're going to shift up 1, let's say 1 is right here, and then amplitude is 1. So we're going to also go. This is 2 and then 0. So our midline, and this is always helpful, is to draw is right at y equals 1. Sorry, that got a little messed up there at the end. Okay, and then we're going to draw in cosine like we're used to doing. So cosine starts high, right? Cosine starts high, then goes middle, except we have to realize that we have negative cosine here, okay? So instead of starting high and then going midline, bottom, midline, top, we're going to start at the bottom. So we actually have our first point. This is going to be right here at pi over 4. The next point is going to be at the midline here at 3 pi over 4. The next point is going to be up at the top here at 2, so 5 pi over 4 comma 2, 7 pi, back to the midline here. Sorry, that was a mistake. I don't know how to fix that easily. Of course, I just erased everything. So then we have 7 pi over 4 and 1, and then we'll be back down at the bottom. Okay, and we can sketch this in. We are going to delete it later, but this would be the graph of cosine, negative cosine of x minus pi over 4 plus 1. Okay, now wherever we had a cosine value of 0, which corresponds to where it crosses its midline, we are going to have a vertical asymptote. Okay, and wherever we had these maximums and minimums, we had a shared point. So we have a point right here that is on the graph of the negative secant function, right here and right here. We can draw in these u's. Okay, so we've got like that, and this one would go off this, the other direction. This one is going to do this U shape, okay, U shape, and U shape, and U shape. I think this kind of looks like a squid, the graph of secant, but maybe that's just me and I am weird, so that's probably doesn't look like a square. So last step then is to get rid of this graph of cosine, because that is not part of the graph of secant. And there we go. That is how you would graph secant. Now, neither the cosecant graph we graphed before or the secant one, neither of them are particularly easy. Okay, so this is fairly complicated versions of both cosecant and secant. So you could, if you get a simpler one, hopefully it's within your wheelhouse now. The last thing we got to talk about here is cotangent. Okay, cotangent is very similar to tangent. One thing to keep in mind is that the fundamental period, just got deleted, fundamental period of cotangent is pi. Okay, and so it's the same thing for tangent. Okay, you can think of this two different ways. You can say that the cotangent of theta is equal to 1 divided by the tangent of theta. And so anywhere tangent would be, just like same reasoning we had with the previous problem, with both secant and cosecant is whenever tangent is 0, cotangent would have an asymptote. Okay, and vice versa too. Whenever tangent has an asymptote, cotangent would have a 0. So you can think of it like that, or you can just kind of think of it just as, you can also think of this as cotangent of theta. Remember, this is a reciprocal function, but or the quotient identity for cotangent is that cotangent of theta is equal to cosine theta divided by sine theta. So wherever sine of theta has a 0, cotangent of theta will also have an asymptote. So you could, for example, right, here's the graph of sine. So it goes something like this. Okay, so whenever sine has a 0, which is here, we had that vertical asymptote there, cotangent, vertical asymptote here, cotangent, vertical asymptote here, cotangent. Let's just jump into an example for this because I think it's fairly self-explanatory. Okay, y equals the cotangent of 3x plus 3 pi over 4. The first thing you need to see here is that this is not a factored out argument, meaning there's a common factor in our in here, and we need to know what is being subtracted just from x and not from 3x. So to do that, we want to factor the 3 out of this argument, and we're left with x plus pi over 4. Okay, this is just a simpler way for us to identify what the phase shift is going to be. Okay, but let's go ahead and take out what the important information is. The amplitude, remember amplitude only related by the sine and cosine. The amplitude is just 1. The period is going to be pi over 3. Okay, it is the fundamental period of cotangent, which is pi, divided by 3, which is omega. So pi over 3. The phase shift is now going to be pi over 4, and since it was plus, the phase shift is to the left. Try to draw an arrow there, it didn't work so great. And then the vertical shift is 1 up. Okay, the tick marks. These are going to be fairly tricky for this one. I kind of just made this problem up, but it wasn't that great of an idea. The tick marks are going to be pi over 3 divided by 4, so they're going to be pi over 12 away from each other. The first tick mark is at pi over 4. Okay, then to that we're going to add pi over 12. So that is like saying 3 pi over 12 plus pi over 12 is 4 pi over 12. Okay, which is pi over, oh wait, sorry, it's a negative pi over 4 plus 3 pi, so it's like saying negative 3 pi over 12 plus pi over 12, so we're at negative 2 pi over 12, which is negative pi over 6. Okay, so that's our second tick mark. Our next one is negative, let's just keep it as negative 2 pi over 12 for simplicity. We're going to add pi over 12 to that, and that's just going to give us pi over 12. Okay, then we're going to have negative pi over 12. Then we're going to take their negative pi over 12 and add to that pi over 12, which is going to give us 0. Then we're going to take 0 and add pi over 12 to that. That's going to give us positive pi over 12. So we have 1, 2, 3, 4, 5 tick marks. That's all we're going to need for this. And we had a vertical shift of 1 up. So let's do my best here. This might not be that great. Okay, and we had negative values actually. So let me undo that. Let's say this is our y-axis. Okay, so we'll go pi over 12. That's pi over 12. That is so negative pi over 12. That is negative pi over 6, and then this will be our negative pi over 4 right here. All right, then we'll go 0, and we also had positive pi over 12. Okay, so this is all going to be really compressed here, but hopefully this makes sense. Pi over 12, negative pi over 12. Okay, here we have our negative pi over 6 and our negative pi over 4. Right, now cotangent is going to start at an asymptote. If we plugged in negative pi over 4 into this function, right, this essentially that you could do that for any time you want to graph something. If you're curious what the y value is at a certain x value, just plug the x value in. That would give us the cotangent of 3 times negative pi over 4 plus 3 pi over 4 plus 1, right? This is 0, inside the argument is 0, so the cotangent of 0 is undefined. So undefined plus 1 is undefined. So we're going to have a vertical asymptote to start our our cotangent graph. Okay, vertical asymptote. I didn't label the y-axis. Let's do that. We had a shift of 1 up, and we had an amplitude of 1. So that's going to be 2, that's 1, and that's 0 down here. All right, so the next point that we're going to get is actually going to be right here, negative pi over 6, comma 2. And the reason for that is that if you think about what tangent would be at a 45-degree angle, it would also be, it would be 1. So cotangent would also be 1. And if this is confusing to you, which I suspect it might be, you can plug in another point. So 3 times now negative pi over 6 plus 3 pi over 4, okay, plus 1. What would this be? So think about this, right? The 1 will just add on at the end. So negative 3 pi over 6, if you multiply that negative in, plus 3 pi over 4. So we have negative pi over 2 plus 3 pi over 4. That's like saying, what is that like saying? Negative 2 pi over 4 plus 3 pi over 4, which is pi over 4, right? So the cotangent of pi over 4 is 1. So then we say 1 plus 1 is 2, and we'd have this point right here like we already put. The next point is going to be here. You can get by the same process. The next point is going to be here. And then the last point will be, well, that if you plug in pi over 12, you would find it was undefined, and you'd have an asymptote here. Okay, and then you just complete the graph. And it's very tricky to draw tangent and cotangent, but we do our best and we get something like that. Now this would keep going. Okay, cotangent is periodic just like all the other ones are. So it just keeps doing the same thing over and over again, and on and on and on. So that's it. Those are the 3 more difficult trig functions to graph, but as long as we have some good understanding of for cosecant sine, for secant cosine, and for tangent for cotangent either tangent or sine, we should be pretty well off.